analytics and education in general. And so without, I guess, going into a whole lot of detail, there's something intuitive about looking at machine learning and the opportunities that it provides that to me suggests it's something we need to spend more time thinking about and more time becoming aware of. For a number of reasons, which Chris will sort of get into and dive into, but I think it significantly augments the research toolkits and the research capacities that are available to individuals who are trying to understand data. Another aspect of it is that it helps to make some of the process of interacting with data much simpler. In the activities around clustering and supervised and unsupervised learning can really save an awful lot of time for an individual that's working with or interrogating a particular data set. So this workshop today is just an opportunity for us to hear from Chris. There's not a lot of folks that are well-versed in machine learning and education or the learning space. Off the top of my head, I can maybe think 3 or 4 people, Chris Brooks, maybe Zach Pardos, Vida, and a few others, but there's not many that I would say sit at that nexus of understanding what machine learning is, what it can do, and then what's the impact or the benefit that it has for education. So I'm very pleased to have Chris Brooks come in and spend some time working on this with us this morning. I'm going to be in and out throughout parts of the day, so don't take that as rudeness. I do want to enter, now let's just quickly make sure, because the threshold for a quality social interaction is to have at least 3 Canadians in the room. Could all the Canadians raise their hands, please? Oh, phew, we did it. I may have said
We'll be building a wall soon.
He dropped out. There's no wall in Canada. Anyway,
we're already on this.
Chris Brooks is with University of Michigan, and we're involved. Those of you that spent, well, a couple of you in the back anyway, spent the last couple of days with us. He is the PI on a discourse analysis NSF grant that we've been working on, and so we're fortunate with UTA to have a good connection with University of Michigan through Chris and through Stephanie Teasley. So on that note, I'll turn it over to Chris. I think Chris and Vida are going to keep us entertained for the day, so great to have you here.
Thank you, George.
One of the things, Chris, you're probably going to do this, but you may want to just do some quick introductions, which I'm sure you've already got on your agenda, but all right.
It's like Canadian ESP, we know it. So I take very much, I'm buying into the active learning approach, right? So today is a hands-on opportunity to kind of learn some of these methods without going into math and gory kind of math details, but actually to use a couple of the tools. I guess the general form is I want to talk about one kind of machine learning, classification, and then a second kind, clustering. I think I do them in reverse order. And then I want to spend some time talking about what data you have and would be interested in applying perhaps machine learning to, or traditional regression analyses. We're doing a comparison, and just help brainstorm where it might be an opportunity or where there might be some interesting use of these methods. As George said, I'm Chris Brooks. I'm at the School of Information. I'm also director of our Learning Analytics and Research at our Office of Digital Education and Innovation. And today joining me, Vida, who is a wondrous expert in here, one of Dragon Gasovic's graduate students from Edinburgh. So he'll be here if we need lots of extra help. One of the benefits is that he has lots of war stories that he can share as well when working with this. So I wanted to just run around the room quickly and see what people were interested in, why they would show up to something that's educational, data mining methods, techniques, and yeah, just a little bit of background. So maybe we'll start with you.
So my name's Amy Woodgate. I'm from University of Edinburgh, and I'm working with Dragon and Cheetah and Shaka and so forth. I'm early days on a MSc in looking at big data and forum interactions. So we have big data sets, and that's kind of why I'm here.
I'm Huda Siraj, and I'm in institutional effectiveness and reporting, and my background is in educational psychology, so I'm always interested in anything data, and that's something that I'm really interested in.
Sasha Novruzbaeva, I work for Decision Support Analytics. This is my director. I'm other side of data mining.
I'm Funda Karaknar-Riley. I work with University Analytics, and I am also doing my master's in computer science, and machine learning is one of the courses that I'm very much interested in taking next semester, so I like to see how it's being.
And University Analytics is a it a more traditional BI, or does it include learning analytics and teaching analytics as well? Or?
So,
Well,
very new.
Chris
Yes.
I
just
will ever
started
so
here.
humbly introduce Professor Pete Smith, who is leading this particular initiative. As far as I'm concerned, it's the only initiative of its kind that I'm aware of internationally in terms of the scope and the focus. But I'll pass it over to Pete to tell you about what University Analytics is and the role it plays.
It's a brand new unit, functionally September 15th, actually officially October 1st. Looking at the gamut, so traditional BIS, operational, all the way through academics and learning analytics. We're trying to assemble a pair of offices, University Analytics in close tandem to Link Lab. So what we're really trying to do is look for those synergies between an operational unit and research. So the broader analytics Haskell campus has all of those features.
And so it's BI, learning management system, it's, IR, like, if it touches on data, it's sort of going to sit under the umbrella.
And so how does it work with the IT group, which is often the place where BI is owned or LMS is owned, or
We have a good working relationship
Yeah,
with
okay.
them, but we are not,
kind of a sister
personally, we're
unit?
not dependent upon them. It's, we're in the presidential.
Yeah, okay.
We scope our data ourselves.
Mhm. Okay.
We provide the pool where you play and dig.
Yeah. Ah, that's very, very cool. Very cool.
So I'm Dennis Ignatenko, and I'm working in the University Analytics now, newly formed. So my background is IR, kind of institutional research. I've been doing that for about 15, 17 years. So it's very interesting.
I'm a doctoral candidate in Vietnam University, and I'm a business scholar.
What's your doctoral program in? Like computer science or business, education?
Educational technology.
Ed tech? Okay.
Good morning.
Mornings, right?
You're next.
Yeah. Just do a quick intro and why you might be interested in machine learning or educational data mining or other cool stuff I might just randomly talk about.
I'm interested in everything.
Good.
My name is Troy Campbell. I'm a postdoc researcher at Lake. My focus is on mid-market outcomes of college graduates. And I'm interested particularly in data mining.
I'm George Siemens. I'm with Link Lab here, and as I mentioned earlier, quite interested in the ways in which machine learning and AI approaches can influence how we're conducting research right now around educational data.
Tristan Nixon, I work at the University of Memphis, currently develop the metrics platform. I guess I describe myself as a data engineer, formerly of Carnegie Learning, one of their big data management systems, hanging around the Indian community for a while.
I'm Mia Dow. I'm at the University of Memphis. Do lots of educational data mining, so I think this is
Great.
I'm Justin Billinger. I'm the research coordinator for the Link Lab, and I look at data a lot right now for research.
Okay, great. So I want to, I'm not going to focus too high on theory. I'm going to try, there's a couple of methods that I like because they're clear, I think, to explain, and people can kind of visualize them, and those are the methods I like to work with, in part because they're actually quite reasonable to use for educational data sets as well, and they get the job done nicely. At a computer science or an EDM data mining conference, you might often find a little bit more advanced methods that are a little hard, things like Fourier transforms and so forth. I'm not going to focus on those. I'm going to cover two techniques in particular that I think are clear to understand and demonstrate some of the benefits. One is called k-means clustering. The other is called J48 decision trees. The J48 just makes it seem really cool, so I had to include that. This is an amazing book. So the toolkit I'm going to use is called Weka. It's open source, it's free. It's also been acquired by a company as their BI engine, and that's Pentaho. I don't know if you've heard of Pentaho. It's kind of in the BI space and is trying to break more into that. And they have Kettle, and there's a bunch of things. Weka does all of their heavy lifting underneath. This book, written by Ian Whitten and Franken Hall, is excellent. It is mapped directly to the version of Weka that you end up using. Every time they release a new version of Weka, they have a new book that speaks directly to that. It's an excellent book. Also, Whitten offers a MOOC on kind of his own platform. It's a 5-week course, and it goes over some of the things I'll go over today. And then he actually created an advanced version of it too. And so it's really accessible. And so there's lots of resources to learn about the toolkit I'll show today. Also, Ryan Baker at Columbia has done a MOOC on big data in education. He ran it on Coursera. I think he's thinking of running it now on edX.
He's running it twice a year from here on out.
Okay, okay. It's also all just available on the web, right? The original MOOC platform, the web. And so you can just go there and download things. His is his MOOC is excellent. It's really top notch. It's also intense. It's this is if you want to really dig into educational data mining, this is the kind of thing as a grad student in the area you would be expected to jump into. All right, so an overview of clustering. The question that clustering really tries to answer is how can we use data mining to better understand relationships in our data? What do we do when data is too big to understand just at a glance? What do we do when we don't have an educational theory? And so depending on who you talk to, you'll hear a lot of, no, we need a theory for, or we need to use theory for. I'm very much on the, we need data for, and from that we can build a theory. So there's theory-driven, there's data-driven, both have wondrous benefits and play off of one another. But often when we're thinking of a new technology like lecture capture in the classroom, we don't have a theory. It's only 10 years old. We don't have a deep educational theory already. And what happens when we don't know how to map our data onto the theories that we do have, right? So when we have theories of computer-mediated communication, but we're using Yik Yak, and it's a little different, and we're not sure how to take theories around CSCL and map it to Yik Yak. So clustering is really the grouping of like instances based on their properties. So often we're clustering people, students, based on some features about those students like gender, age, ethnicity, zip code that they're from, the performance in the class, the way they've used tools, etc. And this is a form of unsupervised learning. So what you get out at the end are a bunch of clusters, and a human has to add some sense making to those and say, these are students who are keeners, right? And I'll call them the keeners from now on, and try and do that tie to theory. K-means is a simple and effective method of clustering. So considering a list of students in a 2-feature space, so that just means we have 2 attributes about the learners, a GPA and an age. The goal is to find the best K clusters in it, where K is just the number of clusters. So what what its name really is however means, right? However many clusters, groups that you want to end up getting. Are there interesting groupings of students in this space is a question. So I'll often use K-means when I have a bunch of data and I'm just trying to understand, like, are students similar in any way? Is there a sense in this data? How many students in each of these different groups compared to one another? So if you have a lot of high achieving students that exhibit, so let's say you cluster based on patterns of access to data, and you see one is really high achieving and that gets really exciting, but there's only 2% of your students are in that cluster, that's important, right? Important to understand before you start deploying interventions, policies, or contextualizing in research. The other thing is this is a form of what's called prototypical reasoning and not ontological reasoning. And so in ontological reasoning, we make hard decisions between categories, right? You're a student or you're a faculty. You're a chair or you're a table. In prototypical reasoning, it's much more how much is this like a student, how much is this like a faculty, right? And so often we'll have people who are ascribed to a cluster. They seem like other students in there, but they're not exactly like the prototypical student in there. And we see this a lot with actually MOOCs, right? When people say, oh, we all know that people who are coming to MOOCs are from North America and already have a higher ed degree. It's just not true. That's just a big chunk of people, right? There's a lot of people who look like that. A lot of people international and have a higher ed degree, right? A lot of people are from America and don't have a higher ed degree. So it's important to be able to understand how well your students fit with these clusters, and the very prototype of the cluster, the thing that you would hold up and say, okay, this is what this cluster really is called a centroid. And people in that cluster, you might have nobody who looks exactly like that centroid. In educational, clustering models are usually descriptive models. They help us to understand the interplay of data with ed theory, but they're not predictive models. So you'll hear about ed data mining and learning analytics and predictive modeling. Usually clustering is not used for predictive modeling, but instead it's used more for a sense-making activity ahead of time. The second technique I'll talk about, classification, is used for predictive modeling. Right, so if we wanted to do k-means on some data, let's say we had these students and they have a GPA and they have an age, we set k as the number of clusters, so we say, okay, we're gonna look to see what the top, what are the 3 clusters in this data. We randomly assign values in this 2 space, in this age GPA space. We randomly assign values, k, 1, 2, 3, and then we associate each data point in the data set with the closest k. And these form clusters. And then we start calculating the centroid of the cluster. I got a great visualization beta coming.
Okay.
Just FYI.
Just for
yeah. And then we create the centroid, and then we start moving the centroid around to develop clusters. And we do this until something called stability is achieved. So I want to just show an example of it. Right, so here's, okay, here's an example, and on this example you can see, like, this is a 2 space, so you can say age is one vector, GPA is the other, and people are plotted randomly in this example. And we have chosen here k is equal to 5, so there's 5. We're looking for the best 5 clusters, and we just randomly drop 5 points on the map, right? And then we associate that's odd. I might need Vito to drive.
You see now? Your fancy technology.
Your fancy technology.
He's more into prehistoric machine learning. Those Serbians.
You can do some clustering with those
Yeah.
Yeah.
Oh goodness. All right, so we've got five random centroids that we've chosen. We just associate the point. A point is associated with the closest centroid. So we do a step, right? So these are now our clusters, and they're colored. So we have a blue cluster, a green cluster, a pink cluster, a yellow cluster, and a red cluster. And what we're going to do is we're going to move the position of the centroid to be a point that is as best distributed to the points in its cluster. And then we're going to do it again, right? So we move these to the center, and then we see, oh, that's changed the distribution of who's clustered where. And we just keep doing that until some stability is achieved.
How do you define some stability, Chris?
There's a couple of ways, but usually nothing changes, right? So you have an iteration where you moved the centroids, and then no new points have been assigned to it. Yeah. There's a couple of caveats with this that are interesting, but it is actually pretty good at in picking up patterns. And of course, I'm just showing it in 2 dimensions here, but it's an n-dimensional method. So you can use it with as many different attributes as you want. So you could add in, gender, age, GPA, college, etc., and you cluster across all of those attributes at once.
You have to have, the more attributes you have, the more data points you should have.
like a normal.
Yeah.
Yes.
Yeah, there's definitely a challenge of power if you've got lots of attributes and very few instances.
The problem is if you have too many attributes, few instances, everybody's too far away from everybody. It's just, like everything is so spaced out, almost the same difference from anything. They don't make much sense.
It penalized, so some of those clusters were small, and I guess I'm mapping. I've used like in the past, but it was a long time ago. I'm thinking about factor analysis or PCA when you get penalized, not penalized, but as your groups smaller and smaller, it's less meaningful, and it explains less variance in your
Right. So you don't, but you have to be careful about that, and I'll touch on that here. Yeah, and how you might be careful about it. There's a couple of methods I'm going to show. Again, keeping with my theme of trying to show the easiest and most explainable, but there's a number of different methods. So the pros, it's fast for even complex data sets. And I had a colleague I was showing this to, and I said, hey, what do you think? I'm giving this tutorial for ed researchers on educational data mining. He's a computer scientist. He's like, K-means isn't fast, it's horribly slow. And I'm like, what are you talking about? He's like, well, if you have 1 billion data points, I'm like, if we have 10,000 students and we have a dozen attributes, he's like, oh, yeah, that's a small data set. So right, a lot of this is contextualized to the kinds of data that I use it on, which is education data. But it's fast for even complex data sets that we would use. And it's really easy to interpret. You can understand at the end what the cluster space means. The cons, it's actually very sensitive to the initial values that you choose for k equals 1, 2, and 3. So if you put 4 of those points all side by side one another in a corner and 1 over on the edge, you'll end up having weird clusters. And that actually is a big problem with k-means. But because it's fast, I use this in my argument with him, because it's fast, you just run it n times. So you run it 1,000 times. It's not unusual to run for one value of k to run it 1,000 or 10,000 times. It's just a parameter in Weka. It churns it out and it gives you the best result. And because it is a descriptive statistic, that's a totally reasonable thing to do. You don't have to worry about something called overtraining, which you do in classification. I'll talk about later. It's not always clear how you choose that initial k, though, right? You have to give it how many groups that you want, and how many clusters do you expect to find. Now, here's where ed theory can help really drive it, right? So if a discourse theory, for instance, says that there will be 3 different kind of positions that students will take. They can either, I don't know enough about discourse to say that, go into that, but there's 3 different positions that they might take in a classroom discussion. We just want to see how many are in each category. You might try k equals 3, but it's not enough to just do that k equals 3. You want to do k equals 4, k equals 2, right? And you want to expand out. Of course, you could also do k equals n. So this is where the number of clusters is equal to the number of participants, right? So if you have 1,000 students, you do k equals 1,000. You get no error because everybody is in their own cluster. We're all beautiful flowers growing in the garden of life. Everybody's special, right? This fits. But so the point is that while this is always going to give you the results of kind of it's going to give you some results of best clustering for various levels of k. You still have to interpret what that means. So there is something called the elbow. There is something called the elbow method, and this is the easiest method to just get a glance and a feel for what the right k is. So what you do is this is the value of k here. So you start with k equals 2, because of course k equals 1 means that we're all just in the same group and it's not interesting. You start with k equals 2, and you determine how much variance, how far people are away, essentially. And so if you think back to the 2-dimensional plot, it's the Euclidean distance, the average Euclidean distance of points squared, right? Root means error squared. How far people are away from that center. And so we do that for k equals 2, k equals 3, k equals 4, etc., right? For some relatively large number.
For n, it becomes 0. Everybody's own point distance from the center for itself is 0. 0 plus 0 plus 0, all the distances for all n points divided by n, you get 0 distance. It's the best clustering,
Right. Beautiful flowers. We're all just beautiful flowers. And you look for an inflection point, and you look at, so this is why it's called the elbow, right? It looks like an elbow. And you look for the inflection point, and that gives you the thought that adding more clusters doesn't necessarily improve the results. But it's important to know this is an understanding or a depiction of granularity. That is, if we use k equals 3, we might get in this room, right, with us just as people as attributes. If we use k equals 3, it might come very quickly down to, oh, there's Canadians, there's Americans, and there's non-Canadians and Americans, right? There's these three groups. If we switch to k equals 2, we might be clustered, oh, there's men and there's women, right? These are different perspectives by which we could group people in this room. And the same is true with our students and the attributes. So if you throw k equals 5, you might be getting a different interesting clustering than when you do k equals 3, which is an equally interesting but different clustering. So it's not that you can't have two that are both interesting and unique. So you really have to end up digging into. Yeah.
Like scree plot, that same kind of idea as a scree plot.
I don't know. I don't.
When you do like exploratory factor analysis.
Yeah.
Yeah, very similar.
Is it? Exploratory factor analysis?
Analyze where there's no value in adding more.
Yeah.
And there's also, just like you were saying, you can have, 8 or 5, and they mean different things, and they're still interesting. It just sort of depends on what you're looking for.
Right, but you'd look like at the variance and the scree plot, and
Exactly.
then that's what you decide if you want to do like 3 or 4 group or.
Yes.
So this is
Yeah.
the simplest method. Like
Yeah.
by determining the number of clusters, you're kind of deciding what level of variance is interesting for you for that level of cluster.
It's also the same, similar thing in dynamical systems. Basis or iteration.
Yeah.
The point in clustering in general, there are no good or bad clustering. All are correct to according to something. It's just which one when you pick, and that's the one problem. Is in general, no method can tell you this is the best clustering. You can't bring any researcher to tell you for your data what, because there's no such things.
And part of this is where you need to tie it then into your theory, right? And this can be theory producing and theory confirming. It can attack theory as well and say, well, that's, as far as a clustering, that just doesn't seem as clean as another clustering, which might be, a different effect going on. But so this is really a part of the sense-making activity. Okay, so I wanted to give a hands-on example back to the whole active learning. Synthetic lecture capture data sets, I've added 2 of them. They're in Drive. Each student in a course has either watched or not watched at least 10 minutes of video for a given week. So I'll just pop that up.
Yeah, you can use it for different types of variables. So continuous variables like age or height or whatever. You can use it for categorical variables like, male or female and things like that. But often you will need to put them on the same scale, because if you're calculating, depending on the Euclidean distance, you're calculating the geometrical distance. Problem is if one is in millions of something and the other is in 1 and 0. The one that's higher magnitude will be more important. You scale them to the same, like do a log, from 0 to 1 or minus 1 to 1. Like that.
This is an example of the data file. So here, this is actually quasi-synthetic, like I did research on people's lecture capture. So each row is a student, an instance of a record for the student. I stripped all the student identifiers because they're actually not needed to build the clusters. They're just needed when you want to do something with them. So I've got W0 through WN, and that stands for different weeks throughout a semester. And we had 13, I think, weeks in the semester. And then did they watch a lecture? So yeah, if yes, watched, or did they not watch a lecture? Not watched, right? Very simple analysis that came from our lecture capture system. And the goal was to try and understand what kinds of groups of learners existed in this system. We started with no theory. So, okay, let me just jump to my slide here. I think my next question is, how many K do you think there would be? So like, given what you know about lecture capture, and there's very little theory on rewatching video after the lecture has happened. I mean, it's only 10 years old. Certainly there's some, but given what you know kind of about education, about students, even your own experiences, what would be a good K? What would you expect to be able to see from these kinds of attributes, just if they watched or didn't watch inside of a given week? Okay, so you might want to cluster, like let's say you think that there's going to be 3 different kinds of students: high achieving, low achieving, and mid achieving. And so you'd set your K equal to 3 and say, do the usage patterns essentially, what's the correlation with those, right? Do we have clusters of students, and then do we map those to their final assessment? Yep, that would be one. You have to categorize those though, right? Because we're not doing like a regression analysis. We're not trying to predict the final assessment. We're looking just to see if there's groups of learners that are similar.
And those who are engaged and maybe not engaged and semi-engaged.
Right, okay, so we might think that there's kind of 3 categories of learners with different levels of engagement. Okay, well, so we can dive in here. And so if you open up Weka, you click on Explorer.
Everybody can do that?
Yeah, if you want to follow along and do it, you'll learn 1,000,000 times more. Guaranteed 1,000,000 times more.
Question while I'm working on this. So I've done cluster analysis with SPSS.
Yep.
This sounds very
Yeah, well, yeah, cluster analysis in SPSS probably uses this method or a similar method. You can use R to do this as well. Yeah, lots of tools do this. So it's not limited to Weka. More statistical packages have picked it up. It comes out of the kind of computer science world more, so, but a lot of this, especially something like R, a lot of the statistical tools now are
How is it different than mixture models?
Just put the name of the file. Just
classes?
click on the, click there.
Something.
No, click on your Excel file to see the
15
clustering. 15 clustering. 15, yeah.
Classes.
mixture model. I don't know. This is, where does this come from? This is
It's more with from like structural.
Oh, okay. Yeah, so this is an interesting disciplinary difference coming from a computer science side versus a statistics side. So I bet you Nia would know much more coming from her background from the statistics side. I've done structural equation modeling a couple of times, but never found it with the kind of data I wanted. It wasn't giving me what I was looking for. Right. So and this isn't
it's very much predictive modeling, and that's
right.
That's what we're doing.
And so I think education is facing now a question about whether to teach what I would say computational methods. So it's K-means and J48 are both computational methods versus statistical methods. And I want to talk a little bit at the end about regression versus classification and how they're similar, but how they're different as well, especially in how we determine whether what we've got is a good model, right? When you get a regression model, how do you know if it's good? And there's a different test in computational methods, and I think there's a substantial difference between the two, and so I'm hoping to kind of suss it out.
I've read a little bit about computational. We used a lot with cognitive psychology. They use a lot of computational, but that's pretty much what I know.
Yeah.
And I went to a data mining class where they would do things decision tree status.
Right, so J48 are decision trees. Yeah, so they're the same thing. J48 is the method by which the tree is created, but the end result is the tree. Yeah, so I'll touch on that. Okay, so what was I going to? Weka, right, so from within Weka, you click the Explorer button, and it will pop up this window here. Make that window a bit bigger. So Weka is a tool created by computer scientists, so it's ugly, and it has some perplexing methods of interacting that you have to get a little used to, but we'll just start in here and see how it goes. So we'll open up. You click open, and then you change it to CSV data files. So Weka has its own data file format called ARF. I don't know if Wekas, which are these little birds, it's in the lower right-hand corner here. This is a bird in New Zealand called a Weka. I don't know if they bark like dogs, and that's why they call them ARFs. But choose 15 clustering, open, and there we go. So it shows you your data, and it shows you the distribution of your data amongst the different classes. I have 2 classes, not watched and watched. For week 0, lots of people didn't watch, and a couple of people actually watched. For week 1, okay, we see a few more people watched, etc. Right? And so we have, these are the different weeks and how much they watched. Okay, so then we click the cluster tab here. We change our cluster to simple k-means. Then, and this is one of the perplexing design choices, you actually click on the word simple k-means and it pops up all the configuration opportunities for it. So that's, I'm not really sure why it's chosen. But you can see here this iterations, that's by default 500 because it's very fast. You can have different ways of measuring the distance if you think Euclidean distance isn't the one to use. And then you can have a different number of clusters. Seed is some random number that you can choose, and that just chooses where you're going to start your initial points. And so the nice thing is about that, if you get some weird value, you can share the seed with somebody, and even though you're supposed to start in random spots, they'll be able to see the exact same thing you see.
The numbers where you're going to put the generated randomly based on seed.
Yeah.
So every new generating random numbers will be the same if they all started with the same seed. So you can predict random. You share that with somebody, and even though it's a random start, they'll get the same random start as you did, and you'll see the same result.
Which is a dense topic, predicting randomness. Okay, so you just click the start button, it finishes quickly, and you get your model over to the side. So what Weka tells you here is how many instances. So in this case, it looked at about 260 students worth of data. These are the attributes. It used 18 different attributes. I guess this was an 18-week course. And then these are the clusters. So the first cluster it found, cluster number 0. That's how you could tell, by the way, a computer scientist wrote it, right? It starts with cluster number 0 and not cluster number 1. Has 64 people in it, and this is what it looks like. Cluster number 1 has almost 200 people, and that's what it looks like, right? And so we can imagine with a k equals 2, we get people who didn't watch at all. That's a big cluster. Okay, that kind of makes sense that there's going to be people who don't use the technology intervention at all. And then some people who tend to watch kind of in this middle chunk, but not at the beginning of the term and not at the end of the term. We also get this value here, which is how well people actually fit to that cluster. Oh, actually, do you want to write these values down?
Which one?
The 664. And that's for k equals 2.
Does anybody need internet details? K equals 2, right?
Yeah. That's 664.
664.
So you can see these are just cluster 0 and 1, right? So it's up to you to decide to label them as to what that meaningful pedagogically, I would say that the cluster number 1 we could call non-participants, and cluster number 0 we could say during class or something like that, during the core of the term. But it's up to you depending on how you're going to use it. So we could just change the number of clusters to 3. We can recluster. We now have an error of 607. We see that there is, again, we have basically a cluster of not watched. So these guys, it says that there's, in this cluster of people who don't watch, that's about 60 people big, there's 1 lecture week that they actually watch. Then we have another cluster here, 1 that has 150 people in it, and they're kind of not watched throughout the whole term. And then we have another cluster here, which seems to be similar to before, which is these people who are watching throughout the kind of core of the class. So what's going on in this cluster? These 2 clusters are pretty close to one another. Sorry?
0.
No, 1 and 2. Clusters 1 and 2 are very close to one another. There's
1 class that they don't watch.
Well, there's only 1 class that they do watch.
Yeah, I'm sorry. That's
Yeah. And so, and this is, remember, weeks over time. What's likely going on at that time? Midterm. So these are students who use the technology just before the midterm, cram for the midterm by watching video, right? And so it's kind of interesting.
Can I ask a quick question?
Yeah.
That second column where it's full data, is that the predominant characteristic for
Yeah.
Yes.
everybody? That's how it gets picked up.
Yeah.
Yeah, but that's what, like when they say for university, typically a student is female, 22-year-old, and so that's basically finding a prototype in all the data.
It's equivalent to k equals 1.
Yeah, k equals 1.
It's never useful. Okay, so let's amp this up a little bit more. Go with k equals 4. So we still see we've got 2 clusters here. They haven't changed much. The people who just generally don't watch, the people who watch during the midterm. We now have a set of people who don't watch in the first 3 weeks and don't watch in the last 4 weeks, but tend to watch quite regularly. And then we have this cluster here, where there's a bunch of not watching interspersed with watching. And this one seems less clear to me kind of pedagogically what that would be, why that cluster looks the way it is. 571, you got it.
It might just be that it's like everything else.
Right, it could be, right?
The others are the meaningful clusters, and this is just
That's right.
Noise.
Because if you just randomly watch in a week or not a week, you could actually be assigned to a variety of different clusters, and you're just somebody on the periphery, right? You're not close to that centroid. And that's why you have to kind of keep in mind that error as you're going through. Not just the overall error, which we've been talking about, but then when you want to actually do an intervention, you want to keep in mind the individual error for that student. Oh, this student really looks like none of our centroids. Let's choose what to do purposefully because of that. So I changed it to k equals 5. So here we have these 3 clusters seem to be the same, 2, 3, and 4 seem to be ones that we've seen before. You see the ordering totally changes, right? I mean, they're just clusters with a number. You have to add that intelligence or that sense making.
3 was now 2, in a sense, that just,
We see a cluster of 18 people here where their closest pattern or their best pattern seems to be they watched on week 1 and then never watched again. So you can imagine kind of from an ed theory that these are people who maybe they try new things, but they get frustrated easily and they leave.
Or drop the course.
Was a site, genius, watched, I know this.
Yeah, this isn't worth my time, right?
Yeah.
This definitely. There's lots of potential for why this cluster is what it is. You got 555. And I'll do one more with 6. We're not going to go to 260. And we see with 6 that we start to break down into very small clusters, right? Some of these have 16 people, 15 people, etc.
Run it to 559, just with all of them, to see the numbers. Run with this. Just put
You want to run it to what level?
259.
259. Oh, yeah.
I mean, just you'll never do that, but just as a, okay, all the different clusters.
Where's the number? 0, right? So
error is 0 because now everybody's in its own cluster, no distances and so on. So
yeah, they're not actually quite all on their own cluster because a lot of them look exactly the same, right? Because there's only 13 attributes. But as your attributes grow, like if you had 10,000 attributes about a student, you would expect them to be in their own
yeah,
cluster.
you can see 9 are not what 9 guys just did that thing.
Yeah.
And
so, but you'll probably have, I don't know how many clusters there are, but you'll probably have permutations of all, right? This is not something you can make sense of.
yeah, but just as illustration at the end, you can
Because the not watched is going to be identical.
yes,
Right.
When you go to the end, it doesn't actually, you put in 259, but it didn't give you 259.
yes,
Because there were people that were identical. So it
Yes.
just gave you
As many as
as
they
many
have.
distinct.
Yeah.
Okay.
Okay, so we have these pieces of error, which is nice. Go back to here. Yeah, no, go ahead.
No, I think you're about to say it.
Okay, so this is how we would draw, oh no, that's the previous one. So this is a kind of hands-on example of how you would calculate the elbow, right? You just take the amount of error divided by the number of clusters to kind of get an amount of error per cluster being added. You draw your line, you choose your where your elbow is, and that's usually a good place to really start trying to make sense. Here, the elbow is not very pronounced, right? Is it 3? Is it 4? I mean, this is a heuristic. It's not a law. So it's up to you to really decide what you're going to use that for and how accurate your clusters are. And again, 3 and 4 are both correct in that those are, the clusters that exist for 3 and 4. It's just, how does that map to your theory? How does that map to what you want to do with it? There are some other methods. Do I talk about them? No. So there are some other methods that are used. A common one is
yeah. There is every clustering is about this. So that's the norm. But let's say your data looks like that. You have these many data points, and now you have data points like that. How would you draw 2 circles? So it starts with K here, draw 2 circles, and eventually you get the weird, because clusters need to be circular. You can't have a cluster that center and the other cluster that goes like a cloud over that. You can't do that with K-means. More fancy methods can do stuff like that, and that's all about clustering. Really, all the fancy methods are just for that. Or the data is like this, like 2 lines. You can't do K-means. It will be like one cluster is here, the other cluster is there. And EM, that the neural clustering, it can do stuff like that. Like you have clusters that are weirdly shaped.
Yeah. It's the same with like linear regression, right? The assumption is that you're looking for, you're only going to find linear relationships or understand that. Once you start to relax that, you start to use other methods to try and find different relationships. So I know Zach Bartos uses spectral clustering, right? And that's the idea here, is to get things that are tightly adjoining to one another. EM is nice because it can, there's some other hill climbing ones, and the idea, the intuitive idea of those is that you have this sheet, and that clusters are like peaks on a mountain coming off of that sheet. So if you've ever like gone and looked at a mountain range and said, hey, I'd like to count how many peaks there are, right? 1, 2, 3. Okay, there's 3 big peaks. But any boulder sitting on a surface is technically a peak, right? It's just got a local maxima, we call it. And so those are different methods for trying to determine how big your peak can be. And so there's a number. And in fact, Weka is actually nice in that you get to play with these. So you're not limited, of course, to K-means. You can choose EM. Actually, EM's the default. And I just won't set anything. It's not wicked fast like K-means, but here actually EM's interesting because the EM inside a method inside of Weka actually will give you the number of clusters it thinks are ideal for that. So
when you say EM, it's EM with like mixture of Gaussians.
Yes, mixture of Gaussians. Yeah, exactly. So what it does, imagine that you have data like this, age of student, and you see the data goes like that. It can be one distribution, but it's more likely that there are two normal distributions that are overlapping, like males and females or whatever, and two clusters. And you'll say, okay, if there are two clusters, can two distributions fit the data? Yes. If you put three, it won't fit. So you'll say like two fit this shape best. Or if the data is like with three hills or something, it will find the best combination of that's it.
Yeah, no, so there's a number that you can dig into. So that's kind of clustering in a nutshell. What it does, and the easiest method, the very first method you'd ever learn in clustering is k-means, because it's kind of I think a little clearer, and there's nice visual tools for it. Oh, this is so weird. Okay. Okay, so I want to change gears a bit and talk about classification. So the goal of classification is prediction. It's a lot more similar to regression. Regression, you're trying to, create a model in the end to try and usually predict some continuous value. In classification, you're creating a model, and your goal is to try and predict some categorical value, right? So are they going to pass or fail? And you can use, of course, logistic regression to do that. That's part of a classification sort of approach. So it's done in a supervised manner in that you have to give it training examples. So the way classification usually works is that you say, okay, here's my data set, and this person passed, this person failed, this person passed, and you just do that for, let's say, half the data set. You say, now, classify the rest for me. Learn the hidden rules in the data that will actually go about and
based on your attributes.
Based on the various attributes or features that we're using. Yeah. So the training data and your choice of training data is important. The rules, I don't want to stress the word rule because it's used in a couple of different contexts in machine learning, but you can think of it as patterns, and that it's a supervised method. Linear regression, straight out of kind of statistics, everybody uses some linear regression. I want to talk a little bit at the end about how some potential issues with linear regression versus classification, and when you might want to choose or think about the methods approach. So I'm going to focus on one that's called C4.5, and the method of the actual implementation of it that we'll use in Weka is called J48.
Why is it named that?
Right, so C4.5, this was the 4.5 version of the algorithm that the individual created. And it's a classifier. J48, because Weka's written in Java, and they say they're actually working with C4.8, and they wrote it in Java, and it's the 48th implementation. It's really unfortunate. But in the end, people usually just, regardless of the method by which you're using to create them, these are decision trees. The output is a decision tree. And decision trees are nice to understand. Like k-means, they're pretty straightforward. So the way the algorithm works is it attempts to bisect the instance space at each time. So if you've got 100 people, it's looking to cut that 100 in half and recursively then work on each part. It's this form of algorithm, a divide and conquer style form of algorithm. It stops when each instance is in the instance space of its class. And so you get this nice tree. And then there's techniques used to try and make the results a little more general, to not overtrain, which I'll talk about briefly, by pruning the tree back. And then the tree metaphors start to grow. Start to grow? Okay, I tried. The end result are decision tree rules. So here's an example of a decision tree, right? If your ethnic background is 2, whatever that is, and your distance from campus is close, and you're wanting to transfer college, and your high school admission average is less than 91, then you will probably be a weak performer. So these classes ahead of time, weak, moderate, strong, weak, strong, those are things I knew. I said, this person is a weak performer. Well, it was really, I just mapped GPA or something like that onto it, right? And so for about a third of the data set, I said, okay, these are weak performers, moderate performers, strong performers. Then tell me the tree. Show me, describe to me the rest of the data set and evaluate kind of how well these rules here would predict on future data sets. We can see if your distance to campus is far and your high school admission average now is less than 85, then you're a weak performer. But otherwise, you're a strong performer if it's greater than 85. These are the kinds of rules that you'll see from the trees. J48 predicts categories, not continuous values, right? That's a big difference with regression. It's also relatively fast, and again, my colleagues like, you use the word fast too quickly, he said.
Too quickly.
But it's relatively fast, and it's easy to read, right? And the end result is that it's easy to program, too. So once you've built the decision tree model and you get those rules, you just write a little Java code, Python code, whatever you want to classify future students and actually build something. And I think that that's important in ed tech. You don't have to hire somebody with a PhD in computer science to do deep learning and build these nested neural nets, right? These are rules you can take almost into a boardroom, maybe not quite, but rules you can use to prepare that presentation anyway, and then to actually build in and link in software. It's not always clear how to interpret misclassifications. And so like clustering where you have this centroid and then you have people at the far periphery, with classification you just have errors, right? Oh, you're a strong performer. Then it turns out at the end of the term, no, he was not a strong performer. There's some latent variable that we don't have in our model, or our model is incorrect in some way, and this person has been misclassified. And that's kind of a key point with each result of the mining process, is to determine which paths in the tree, we'll call those rules, which paths in the tree have high classification accuracy versus low classification accuracy. There's multiple ways of being wrong, and some are worse than others. A good single number measure of accuracy is something called Fleiss's kappa. If you do psychometrics and traditional stats and inter-rater reliability, then kappa might be well known. And for a more in-depth consideration of how you're wrong, you have to look at something called the confusion matrix. Usually I try and say matrix in like a low voice. It's starting to get aged. So a hands-on example, there's a synthetic lecture capture data set. And so we'll give a quick example.
And that's been done by, for instance, banks. Pick the data from their credits they were given, and are people are returning or not, and they have attributes of all the clients, and they build classification models, and they're, for instance, by law required not to use, for instance, ethnicity.
Right.
And then turns out that zip code is essentially almost the same as ethnicity at least in US. So they're now required to remove those as well. So they're trying to make classification model verse to be more fair, in a sense.
Right, to eliminate some biases they don't think should be included in.
Shouldn't be, maybe.
They use it for fraud detection too, is another example of how classification would work, right? Oh, this was an instance of fraud. Let's log, all the kinds of stores that this card was used at in the last 3 months. See, and then as you get enough instances of that fraud coming through, so you're helping the bank when you tell them your card was stolen and used, not just helping yourself, because they can build better fraud detection methods. Okay, so you open up Weka. We're still in the Explorer. Click Open File, and then I think it's called 15classification.csv. Okay, so this is a little bit of a different data set. Here I've just included 4 weeks. Again, I'm a computer scientist, so I start with 0. Week 0, week 1, week 2, and week 3. Yeah.
Can you show a link where to download files?
Oh yeah, it's right at the bottom here. Bit.ly /link15-tutorial. Yeah.
I do that. When I give tutorials, it's a good keep at the bottom.
Handy. The first run of this. That's where I learned that. Right, so we can explore the data a little bit with Weka. So I want to show you a little bit about, a little more about the Weka interface here. So we see, for instance, it'll tell us the type of data that it's automatically detected from the CSV. So for this grade, there are 3 different classifications or categories: normal, honors, at risk. You can see the distribution of how many people are in each group. And then you can see that this is nominal data. Gender is also male, female, nominal data. Citizenship. Then we have a student identifier. So this is unique to each individual. So you'll see it's type numeric here. This tries to show you some distribution, but it looks fairly evenly distributed because they're random numbers. It tells you actually that it's unique, that there's 100% of the data is unique, right? So this is a piece of data we don't want. We have college, nominal, and then we have these whether they watched or didn't watch, and these are actually zeros and ones. They're not the not watched that I used before. They're zeros and ones. 0 means not watched, 1 means watched.
Yeah, one thing to know about this, sometimes if you have 3 categories, let's say, 0, 1, he's smart enough. But if you have 0, 1, and 2, it can get confused saying it's categorical variable. It's a continuous variable. So you look at that.
Oh, this is what it's done here too.
Yeah,
it thinks it's
here.
continuous.
You think it's a numeric continuous variable. Not
Yeah, because it's dummy coded.
Yeah,
because it's a dummy coded, yeah, and sometimes he's smart enough, sometimes not. Well, in R as well.
How do you change that?
Right. So it's a good question. So you choose under you can add filters. This is for some basic data manipulation. I don't do a lot of data manipulation in Weka, but you can do it here. Filters, unsupervised, attribute. These are all of the different things you can do, and one you can do is numeric to nominal. So this is
what you need.
Yeah. And then you see it says numeric to nominal, and it's going to do it for first to last on this little label, which you click, which again is very weird to do in an interface, but it's a very Weka thing. And then you can just put the range of values that you want to do it on. So right, like 6 to 9. So that's going to change it for these 4.
And those are column numbers?
Oh, yeah.
It's this number here.
Yeah, so column index.
Yep. And then you click apply. Once you do, everything should get a little more colorful, in part because these are now nominal values. So we can explore this data set a little bit more. Down here is the class. That's the thing we're trying to predict. Let's say we wanted to try and predict gender. We could actually look at, well, what's the distribution of gender in college? So here's the distribution of college, where red is...
Mine didn't get color. Can we go back to that?
Yeah, is this what it says at the top?
It says, yeah, R 6 to 9.
Hit apply.
Did you hit apply? Yes. Okay, yeah, so gender, let's say we're going to try and predict gender based on these values. So we look at college. Does college predict gender? It doesn't really look like it. There's 3 different colleges. There's not an even split, but it's kind of the same, roughly the same split by college. Student ID, of course, this is useless number. Citizenship, it looks like there may be something there, right? That at least for these 2 classes, that it's highly unbalanced data. The non-Canadian citizens and the permanent residents, it looks like there's maybe no females in that list. Was female red? No males in that list. Males are red here. And then we can look at our 3 grade categories. And yeah, it looks like there might be something, gender might be a piece of that. We can also start looking at the way different people watch. Doesn't look like gender affects much of how they watch. So you can explore the data just a little bit like this. Of course, SPSS, right? Like there's a million tools to do that exploration. But sometimes it's helpful to do it inside of Weka if you're using Weka just to get an idea. Okay, we want to get rid of student ID, so you just check the box next to it and hit remove, and it's gone. So again, you've got some basic data filtering inside of Weka. All right, and college. If you click on college here, up here you'll see that it says that 7% of the values have no college. So one of the nice things about J48 and Weka is that it can try and fill those values in for you. Essentially, we'll use values as they already exist in the rest of the data set and impute those for it.
Basically, almost doing something like clustering in the background. Clusters, people say, hey, this guy would be in this cluster. Most of the people in the cluster are like, in a public 4-year university. Okay, we're gonna assign you this value because like it makes most sense.
All right, so we click the Classify tab, and then we're going to choose the classifier.
Do you have to do that impute method to run it?
Nope, it's doing it in the background.
Oh,
for
does
you.
it?
So there's a lot of things that we can use under the Classify tab. If you go into Functions, you'll find more regression style things. So you can use logistic regression right here if you're familiar with it, or linear regression if you're predicting a numeric value, and so forth. We're going to jump into trees, and we're going to use J48. And it just gets like J48 graphed, and like there's so many wondrous plant metaphors, I really think.
Some people implement, you know, like small piece of algorithm is different, like, and there's a reason why somebody did that, and they included in like millions of classification algorithms.
Click Use Training Set. That means it's going to build a tree off of the whole data. We're also going to change this drop-down box that is not labeled in any way. Again, computer sciencey. We're going to change that to grade, because we're going to try and predict grade. And then you just click Start. And so here's what our tree looks like. So if they didn't, again, these are dummy variables. So if they didn't watch in the first week and their college was, we'll call that E for engineering, and their gender was female, then they're likely to get honors. If their gender was male with those two rules, then they're likely to be at risk. If they're in either of these other colleges, then they're going to be at risk. If they did watch in the first week, they're likely to be in honors. So you can see how the tree is essentially a multi-level method and not a linear method. This number here, the first number here, is how many people are in that leaf from your data set. So, and just bear with me that it's a weird decimal number. There's some things that are going on in the background with pruning of the tree and generalizing and running multiple values. But so here we have 47 who ended up at this node, and only 5 were misclassified. So that's a pretty decent model. Here we have 51 ended up there, and the error is a little higher, 15. This one seems quite poor, right? We had almost 12 people there, and almost half of them, or between a third and half of them, were misclassifications. I'm not really sure I would put much faith or into that. This then ties down to what you use the models for. So again, a computer scientist at a conference cares about the accuracy of their model and will often just describe the accuracy of their model and say, look, it's 2% better than that model. But actually, you have to decide what is the intervention that you're going to do with this? What is the policy change that you're going to do with this? So if you're going to create, as the College of Engineering, if you're going to create an at-risk study skills program for men, because you saw, oh my goodness, gender seems to change whether you get honors or at risk. Knowing that this is a very noisy measure might help you really consider the trade-off with respect to cost, right? And whether that's something you want to do. So it gets a lot more into institutional analytics and decision-making from that data.
And so maybe you would want to add other factors that might.
Right, so you might want to add other factors and try and suss out what this 15 here is going on. You might want to try and think about, well, so for instance, often if people who are doing well, you already kind of consider them doing well, and there is no intervention. But in that case, you might just want a different intervention that helps you identify in that room more qualitatively who are the people who maybe don't get aren't going to be able to get that. And that's where you could tie back to ed theory, right? Let's say you don't have numbers on first in family, so you can't build a quantitative model on it, but when you're in the room in front of people, you can kind of tell, you can ask people, and then you can kind of shuffle them around a little bit. So you can leverage their quantified values with your kind of a more qualitative and theory-driven methods. We have, so I would say in data mining and predictive modeling has gone through many stages as to how to report how good things are, how good your model is. So in the very basic stage, you'll see companies do this, and they'll say, we have a 90% classification accuracy. I saw a company that said, we can classify with a 90% accuracy to within a letter grade of what a student's going to get. But that's actually really easy. You just look at their SAT score and classify based on that. And yeah, you're wrong for 10% of the people, but otherwise, it's a pretty trivial task, right?
Also for like cancer, like every person, classification 99.9% for cancer is trivial. Just say nobody has cancer because less than 1%.
Cancer's rare.
And you just say nobody has, the classifier just says nobody has cancer, and it's going to be correct. Give him 1 million people, he will be correct 99.9% of the time, but it's total junk, totally useless. Right?
So, this correctly.
I think it's a lot of these cases, you need to go beyond like accuracy. You need to think of the value. Like, what's the value of a true positive and a false positive in classifying? Like, obviously in cancer, a false negative is going to be really, really bad.
Right. Yeah, if you say somebody doesn't have and the guy has, well, he will die. But if you freak out a couple of people to go traditional testing without any reason, you have wasted a little bit of money and freak him out.
Right.
But
so it's not
no big deal.
Right. The value of these things is not symmetric. So sometimes you want to skew your classifier in a direction.
That's right, definitely. And so that's where the confusion matrix comes in, because it tells you that true positive, false negative, true negative. So just as an example, my wife is pregnant and she's due in December, and we went, thank you. We went in for the kind of normal testing coming up to it, and they're like, okay, well, we can do this test, or we can do this other test that's a little bit more invasive and a lot more accurate. And I said, well, what's the chance of complication with that other test? Well, I mean, the chance is quite significant, right? You could lose the baby if it's an invasive test. And I'm like, okay, well, let's do the one that's not invasive but is pretty inaccurate to begin with, right? And then go down other methods. And so I think that's an important thing for us to think of as educators too. Often we think, okay, well, let's create, if I was going to classify people and said, okay, these ones are all at risk, let's kind of push them into this help facility or this help method. If it's an automated help method, like an intelligent tutoring system or an electronic system, why not just give it to everybody, right? Like, how much are you going to hurt the high achievers already by giving them a little extra help? However, if there's a huge institutional cost to it, so a learning community, for instance, which has maybe a building associated with it, and there's only so many room for people, then you have to really weigh in how important it is to accidentally put somebody who doesn't need the help in there, knowing that you might be leaving somebody else out, or you might have other resources for the people who really need the help.
We had a similar issue when I used to work at Carnegie Learning, and we were like training our mastery-based system to assess when students have mastered the material, and you want to try and bias it towards more practice, because I mean the worst is like you waste a little bit of the time. But the worst on the other side is you're saying this student has mastered this material when they really haven't.
That's right. Yeah. Better to have them do a little bit more. And so it really depends why you're classifying and what you think you might do with it. And you can explore, right? Now that you have this classification tree, you don't have to do anything with it, right? This is representative of the data you have. And that way it's very similar to a lot of linear regression methods, in that linear regression is usually used in a way that represents the data totally and completely. That didn't sit well with computer scientists. And so this is kind of a split in methodology, not even methodology, it's more in reporting results. I think the people who are in data mining didn't want to just understand the data set they had, but wanted to be able to predict how well things could work on future data sets. And that's different, I think, than a lot of literature that uses regression. Before I jump into there, though, I want to point, here's a nice one number, because once you have a lot of categories, let's say you have 10 letter grades that you're trying to predict, or 5 different categories, the confusion matrix can get a little confusing. Kappa as a statistic is a really nice one, Pleiss kappa, because it's quick and easy to interpret. It just says it's a chance-corrected number between 0 and 1 of how well were you able to predict. It conflates all of the kinds of predictions together, but it corrects it for the distribution of people in your training data set and what level they were in.
And one other one is F measure. That's also other one. Computer scientists use that one more often. That's a trade-off. If you see here, you have true positives and false positives. So ones that are predicted badly in a category or not predicted in that category, and you calculate F measure based on that. So, and typically, yeah, you know, that's one that you also see all the time in computer science, you know, in papers.
You could see just from the tree, but you can also see from the confusion matrix that nobody was classified as normal. Isn't that great? I would love to live, that's the every flower, right, is beautiful. Nobody's normal. But if we go back to the data, we actually see that there's not a lot of data about normal people. And so sometimes you want to find a way to equalize your data sets for the classification task that you're doing. Subsampling this data set is one way, but I like big data, right? Big data gives you a lot of fidelity. There's a really nice way to boost these data sets. A common technique that's used is called SMOTE, a synthetic minority oversampling technique, where it generates synthetic students that look like other students in that category but aren't quite the same. It's a great method for increasing the accuracy of classification tasks. And you can do it from right inside of Weka, but you have to install it as a plugin. Weka now has I don't know where the plugin stuff is. But you could do it right inside Weka. You choose it as a filter, actually. Supervise.
So that's like you have, 1,000 patients, right, 5 have cancer, 995 don't. You generate non-existing people that have cancer similar to those 5. And now you have data set that's more like, 1,000 people with cancer, 1,000 without.
The class value.
That's logic.
Anyway, it's a great technique to use, and I've used it. It has one problem. When you create fabricated students, then you have to start thinking, well, you really should be thinking about this before, and you do this often with regression too. How do 2 attributes relate to one another? So for instance, if we polled people on their gender and their sex, we would find there's a high correlation between those values, right? Most people are this gender expression of their sex. That's not true for everybody, but most. And so that, high correlation. Or age and income, there's a relationship there as well. So one thing I've done in a data set where I was looking at students who were being admitted to the university, and I wanted to boost a certain group of students, and I ended up getting zip codes that didn't match to the city that they were in, zip codes from other cities, because I had city as one attribute and zip code as an attribute, and I didn't recognize that relationship. And when you use SMOTE, you have to take one out when you're doing that technique. Weka, even with classification, is still pretty good at imputing values though, right? But the zip codes are often seen as numeric values as opposed to nominal values or ordinal values. They're not numeric values from a data mining perspective, because you can't just like take an average of a zip code. That could be a different city. Okay.
But you could do something similar in Canada, for instance, because they have zip code that you could almost like because of A, B, C, and so you could technically
They have
do
letter-based,
average of
yeah.
zip codes, and you will get city that's somewhere in the middle of the city.
Actually, the postal code in Canada is very parsable. So the different, the S means which province you're in, right? So you can actually start to throw away pieces of information and build new attributes just out of the postal code, which is kind of nice. With zip codes, you can do the same thing too, but you need a lookup table to the post office, which is.
Smart keys.
What's that?
They used smart keys for
Yeah.
the.
Yeah, that's right, yeah.
We actually used to use a simple trick rather than, but often when we do finding experiments, rather than kind of randomly sample or like do a random sampling from all possible student data, we'd often just pick schools that had a zip code that ended, the last digit ended. So it was like a fairly random distribution across the country, whatever the last digit of the zip code is. So if you just pick like all the schools that end in 7 or something like that, you get a pretty good random sampling across the country.
Oh, that's good. That's a nice, I like that trick. So
the first digits are obviously quite geographically meaningful. The last digits are pretty random.
Yeah, so
might be heavier distributed towards the lower ones.
Sorry?
It might be heavier distributed towards the lower ones. Like there might be more 1s, 2s, and 3s.
It's possible. Yeah.
But anyway,
I didn't look at
that's
the number
completely
of schools unless it's my last digit.
That's interesting. Yeah. So in Canada, the last number indicates whether you're in a city or a rural area, right? So if you did that and grabbed 0, you'd only get farms, right? But that's a way that you could pull that out, actually. And so we would typically pull that out and say rural as one of our dummy variables, 10, based on what the last digit of the postal code was.
But that looking at digit is one of the ways that banks do fraud detection. I think because I think when people start cooking books and they start entering data that doesn't exist, right? So instead of providing like report generated data or whatever from that comes out of system, when people try to enter data manually, generate data like maybe account balances or transactions. So they will tend to like start with 1 or 1, 2 or 3 or that kind of a thing, and so that's one way they can spot manually generated, human generated data from true data.
Because they make the same mistake of not recognizing the relationship dependence. Okay, do we classify? Yeah. So down here, the confusion matrix is useful to look at. Along here, the top, the columns are what was the classification that the classifier returned to you, the automated process, and down here are the classifications that we know to be true from the fully annotated data set. So we can see that for everybody who was in honors, actually we misclassified 14 of them, and we correctly classified 78 of them. And you can see that this is a big part of that data comes from there, and some of that.
Yeah, you want to have the biggest numbers on the diagonal. That means
Right.
that's correct classification of diagonals or errors.
Yeah. And so ideally your diagonal looks is big numbers all the way. If it's a balanced data set, it's ideal to have it kind of balanced all the way. Those are the different your different categories. Okay, so I'm just going to go off script here and show this. So one thing when you're doing classification is, so one of the ways, I'm a little frustrated with regression and when I read ed papers. And so often there'll be, we collected this data set, we did this giant linear regression, here's all of these betas, isn't life great? And the problem is often all of those betas are used, that's the whole data set that's been used. So you've got 100 students went through, you built the regression model, you've got some error, but does it predict anything for the next 50 students that are going to come through? And I think the general thought is, well, as we get more data, we can continue to tweak this model and get a more representative model. How do you know how well it works? And so in computer fields, especially vision, where you have 100,000 images and it's easy to create and get more images, you start using a holdout set. And so you actually build your classifier on a chunk of images, let's say 50% of the images, and then you test it on 50 images that your classifier has never seen. Take a quick look at Justin there. Yeah, that's not mine. So, so the right. So I'm going to show you how to do that in.
Yeah, the problem is you build a regression model on everything. You get the best betas possible because that's everything you know. But how good they are, you can't tell that. It's just not.
You have the, I agree with what you're saying, but what if you have this is categorical, like you're restricted, right?
Well, you build a logistic regression, you will get some, basic results.
I guess how do you handle?
Yep. So you would take half your data, you'd build your regression model based on half your data, and then you would see how accurate it is for the other. So for a given instance, you should be able to calculate what their predicted grade would be, and you can compare it to their actual grade, and you can kind of calculate all of those numbers and create the level of error. And that's how some
Actual and predicted score.
Yeah, so for linear regression, you can calculate those errors, how far the actual data points are from the line. But you can say, why go linear? And you fit some crazy line that fits everything perfectly. Is it the best regression model? Probably not, because that's fitting the data perfectly, fitting not just the information, but also the noise. Each data point is a little bit of noise. I might be running slow because I'm, a grad student, not, physically active, but also I have something unique to me, that you shouldn't build a model on, some small variation that we don't care about. So that's
the regression models are not used to predict. The only models that are used to predict are discriminant function analysis, and that's where you would predict.
Yeah, but
and like survival analysis, that's when you're predicting. But like regular regression, we're not trying to predict.
You can predict.
We're not trying to predict
I think it's
in
the range
sense
you're
of
trying.
classification.
So when I read ed papers, I often see it being suggested that it's predictive, right?
Yeah, it's predictive, but they're not trying to predict classes. So they're not trying to predict like.
Right. So this technique, we don't have to use just this technique. We can use a form of decision trees for non-classes for predicting.
Regression trees. They're regression trees.
Got it.
It really comes down to
now it's more like
Right.
similar to
what regression is. Yeah.
Talking about the training, validation, and testing.
Right. So if we train on this year's cohort of data, how do we know how well that will predict on next year's? I feel like a lot of the ed papers just stop short of testing that, right? And telling that. One easy method of testing that is actually just train on half of this year's data. And that'll give you a feeling for what it might be like to train on next year's data. Not perfect, because there's other latents that next year's students will be coming in with, right? And so one way you could do this in Weka is you could just do this percentage split. So here it says a 66% split, so it's going to hold 1/3 out for testing and validation, and it's going to use 2/3 to build the model. We see when we trained on the whole data set, the kappa was 0.5. When we train on this percentage split, our decision tree is horrible, and we see that our kappa statistic is in chance, right? It drops way down. This suggests that may have been overtrained. So the gold standard for a while was to use something called cross-fold validation. And this is where you take your data set, you split it up into 10 pieces. You take 90% of it to build your model, and then you test it on 10%, and then you do that again and again and again, always holding out a different chunk. So the idea is to try and determine how general
the idea is you don't want to hold out anything because you're losing stuff to train on, and you don't want to train on everything. So this is like you train 10 times on 90%. So nothing is oversampled because everything was used 9 times, and everything is tested on only once. So you test about all of it, and then you make basically like a average of all 10 models and you say, okay, this is the final model.
I did make a mistake there with the percentage split. Like it seemed like it was totally horrible to me, and that seems weird, right? The problem was when you click on this, the percentage split, when I had gone back and forth between tabs, it had changed what I was classifying. So actually, to classify the grade with respect to percentage split, we see our kappa drops to a 0.58, not horrible. We have, some tree. Our first kappa was what? 0.50, so it's actually built a better tree.
It also depends on the luck, which one you split on. That also build, sometimes you can be more lucky.
And it's just choosing randomly, right? That 2/3 to hold out. Tenfold, you can do n-fold, but tenfold validation, we can see, okay, our kappa is 5.6. We have a tree here that looks interesting, and we can interrogate that tree a little bit. So this, for a long time, I think was enough to get published, right? That is kind of the standard by which you should be building models. But I think things are starting to change now, even as well, to a holdout set that you've never seen before. And so Carolyn Rosé from CMU, who does a lot of this, she has a holdout set of data that she has never looked at and never tested her model on the day she submits the paper. She runs it, and all the stats from that go into her paper. And that's terrifying, right? Because you've written this paper up to this point, you've used these other methods, you're pretty sure that it's pretty good, but it's really this kind of blind taste test, if you will, of what that holdout set looks like. And I imagine if it reports totally ridiculous numbers, she interrogates and panics a bit. But
that's how Kaggle works.
Yeah, it's kind of the point, right? Is that you want, when you're building a predictive model, you're trying to build an engine that's actually predictive on data that you haven't seen. There is
It allows you to cycle a number of times, tweaking your model on and even cross validation on your training set, and then you still have a good validation of the final set. If you spend a lot of time tweaking the model on the training set, even with cross validation, you're gonna overfit.
Oh, for sure, for sure. And sometimes you're doing it without worry. You're thinking about overfitting. You think, oh, what if I put this? What if I put this? Right? And thinking that these are all kind of nicely driven. So I don't see this being done with regression analyses, and I don't really understand why. I'd like to understand that better. I welcome thoughts, but I feel like often regression analyses are going to be used for the same kind of thing, right? We want to predict what students' grades are. We use regression analyses in early warning systems.
There is one thing I think why I wouldn't use that for regression. Regression is very stable. Regression is not that complex. So this model is much more complicated. You have many different attributes. You're basically building a combination of attributes. It's like a
multi-level,
higher polynomial regression.
Sure.
Because you have interaction between the
right,
attributes.
at each level.
In linear regression, it's very stable. Adding a couple of points or removing a couple of points would not affect it, at least linear regression, that much. It's very stable. It's not going to be but one outlier change it so much. This one can change by 2 data points and completely flip it.
Yeah, so that's actually you have some control over that too, because that's where overfitting can come from. Going off down this, and you see here 2 people ended up at this node, and one of them was misclassified. That's useless information, really. So actually, that's a good segue. If you go up here and click on the J48 label, one thing you can do is there's this value for min-num object, and that's basically how many people have to get to a leaf before you don't prune it away. And so if we change that, now what you would put in there depends on your size of your data set, but let's say five people is a reasonable number. Start with that.
Yeah, get something totally different. I mean, it's yeah.
Yeah. You notice that when we did tenfold and started to play and tweak, we're starting to get diagonals.
But you still, B's are horrible. B's are classified as C's pretty much all the time.
Yeah. Yeah. And is that a problem? Maybe, maybe not.
I got something totally different too.
Yeah, you could, the seat
Well,
could
you'll
be
say
different.
that's
or-
not a big deal. Yeah, you're saying the
This is
normal folks are at risk.
random.
So just annoy more people than you should, but
Or you're gonna annoy the advisors.
Right, right. So there's this university analytics side and the learning analytics side, right? That are, right? So
Yeah,
if you have all these normal people that you're sending into the at-risk category, maybe the at-risk category is really high touch, what you're doing with them, and really expensive to do. Yeah, it's a wonderful world, actually, once you start to mix in the analytics, institutional analytics, I think, because unless your treatment scales. If your treatment is cheap and easy to scale, intelligent tutors are a great example, right? If it's cheap and easy to scale, once you built the tutor once, you can deploy it for 10,000 students. Then
yeah, but also
you don't have to worry about
that.
as much.
You might annoy students, but like asking them follow-up questions that they think are totally useless for
Sure.
them because they know that, and like this too, this system is for idiots, it's not for me, and
Yep.
Well,
yep, definitely. What else do I want to touch on?
open up the parameters of that. I think that's good. You can see what else you can tweak there.
Yeah, what do I use? Sometimes binary splits. So that's when you have an attribute that has many values. Do you just split on kind of one aspect of it, or do you have a triple split or more? So that changes what your tree might look like.
So that would be like, so what if you had like a continuous, not continuous, bounded?
Yeah. So usually numeric values that are continuous are binary split, because then they just nest binary splits, right? So you can get kind of, that's usually how J48 works. It doesn't have to for a decision tree, right?
Okay.
Yeah.
The other thing you could do is visualize the tree.
That's cool.
Hi.
Yeah.
And what is like the oval, the circles?
So if we walk through it, the squares are the leaf nodes. That's the final point, and the circles are essentially test nodes, what you would test. So the very first one it says, and the nice thing about a J48 tree when you look at it is in many ways the attributes are prioritized because of the way it tries to split attributes. So splitting on W0 first, if that's the only thing you can do, you should do that. So when you start thinking about how to implement this, if you have a very big tree, and in ed data we really don't, but if you did, you could start to roll things up just for sake of computational efficiency. But in week one, did they watch? If they did, honors. If they didn't watch, then let's look at their college. In their college, are they in engineering, computer science, or in finance? If they're in computer science, at risk. If they're in engineering, then we have to go look at the next week of data and see if they watched or not. If they watched that, okay, maybe they get honors. So I want to try and explain potential hypotheses, right? If they watched first, in the very first, let's say that's like a student orientation week. Not everybody has to watch it. You're not necessarily going to be, successful, but all the keeners go and watch it. So they would fall in this category. And you got a couple of people who aren't keeners, but thought, oh, my mom's making me watch it, right? And so they slid into here. There's a few misclassifications. College, computer science, maybe all the faculty are just really poor in computer science, right? And so here's where you get at risk, right? So you can start to build a story and try and dive into why these are the way they are, looking at bringing in qualitative methods or other quantitative methods. Week one, let's say that's when engineering really, really starts, right? And so if you watched in week one, then you're good to go. And then maybe there's a gender bias for some reason inside of engineering, where women are more likely to get honors and men are more likely to be at risk.
These are really how people think about, like you call your mechanic and they will ask you, okay, can you turn on the car? You say, I can. And so, okay, that's not the battery then. You see him splitting in his mind, doing those kind of things, basically. That's how, and when people say, okay, but it's battery, okay, can you, switch the gear? And he was okay, that might be more likely is that, but he knows about those small misclassification. If it's probably your clutch or something is broken, but it also in rare situations can be something else. Those rare situations are really those misclassification. His expertise come into place at that
Of course,
point.
like the cool things about these, the idea that you could engineer sort of an expert system that can replicate his knowledge, and you can just extract it straight from the data, as opposed to having to spend a lot of time with an engineer.
It's all just learned, right?
Yeah.
So what are the things that he all checked or didn't check, and did the car end up working or not working? And so I like sometimes when I'm hanging out with my other colleagues who are more theory driven and I'm more data driven to say, I'm thinking about doing this kind of machine learning thing, and this is the kind of data I have. And they'll say, well, we know from educational theory. That's always the statement. We know from educational theory, blah, 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 right? I say, great. Can you just draw me what that decision tree would look like, right? How do I, put people where? And then I go and I just do this, and I see how closely they match. Usually they're totally different, but not because their theory is necessarily wrong, but because theory is complex and it's coarse-grained usually. It's things like people in reciprocal relationships are more likely to do better. How the hell do you turn that into, there's a lot of different theories, and this is a very data-driven method.
And sometimes in theory you get like a lot of very fine distinctions, which might be totally appropriate, but they're not representative of a large portion of the population.
Or they're at this level, right?
And another thing, the system can do only what's been trained on. So expertise can sometimes play, theory-driven, that's why, now on stock market, they're not traded by humans, by some computers. And, one change and, a small country can go bankrupt, because of, system was trained on this situation, and 2008, and it starts applying the same rules that were working, a week before, and just collapsing, doing some serious mistakes. That's also a problem where you can apply from. Train on US data, now you go to Africa and use the same classifier. You can make big mistakes. So.
But it's not about proving the theory correct, right? It's about proving or disproving the theory, and then you extend the theory.
Yeah, that's
right. Yeah. So theory is often a place where you want to start and think about, because the hardest thing out of all of this, which we really haven't talked about, is how do you choose which attributes to put in your model? And there's an expense that comes with collecting every single attribute, cleaning those attributes, maintaining those attributes, and that's where I think right now theory has its biggest implications, right? Is making sure that we're picking the attributes, right? So in admissions data, for instance, socioeconomic status and first and family are two things that are often hard to capture. Theory tells us they may be important, and it turns out they tend to be important. And so it's great to grab them, and that sometimes is a split up here. Sometimes, like in this example, gender, it's a split down here, but it's a piece of the puzzle.
Yeah.
So data and theory really should work together, but I would say the community is sometimes stretched because it's an emergent community, right? Of people who are coming from a data perspective, like I am, and people who are coming from a theory perspective, right? And so learning analytics and academic analytics, I think, is exciting because of that.
It's nice to see kind of like which theory is at work. I mean, to look at the data and say, well, I know about these different theories in, how socioeconomic status affects learning, affects achievement, and then I want to know which one is at play, knowing which.
With my population, my system, and my technologies. Yeah.
You need a critical view also. Many of they were building those as for sports betting. You pick all the games that are played in basketball and you try to build a model, and you may end up with Chicago Bulls play on Tuesday after 3 p.m. and in a stadium with 10,000 people, they will always win. Is this does it was just a coincidence in the training data you had that it turned out they never lost a game if they play after 3. What's different between 2 p.m. or 3 p.m. There is no difference. So you need to be very critical, and that's where theories are really good, because those things don't know anything about what's actually happening. So you're like, okay, this classifier is
That's what I'm
totally,
saying. You use your theory to guide what makes sense.
Exactly. You cannot.
Outcome, and sometimes those are actually, you get unexpected real effects. Like there was a study a while ago about it was on like decisions that judges would hand down, and it turned out they handed down more favorable decisions after lunch.
Sure.
So suddenly there was a rush, like everyone wanted to schedule it, they're happier after lunch.
There is a great
8:30 a.m. classes, right? We've all been there.
You see, that's why I said yesterday at our workshop that research should raise questions more than it answers.
Yes, I agree. And it should be a continuous cycle, right? Where data is informing theory, and theory then informs data and data collection.
There was one in the shopping analysis of shopping habits. They realized that people who were buying diapers were more likely to buy beer. And it's not like why that makes sense. You will think it doesn't make sense. I would discard it. But it turns out there is a logic. You're staying at home. Those people are like, well, okay, I might as well buy some beer, watch a game when the child goes to sleep or something. But there is, some of them we know, like if you buy hot dogs, you'll buy ketchup. That's, that makes sense. I mean, but some things you learn that no, theoretical, market researcher will ever come up with, because it's just totally bizarre to,
Buying guns.
Yeah, if you're next to buying, that's not that expected.
And that's another reason why you really have to keep that that issue of training data and holdout set around, because overtraining is a huge problem, especially when you don't have a lot of data and you start to generalize decisions off of a very small collection of data. We're kind of living in this awesome big data world in education now, especially when we start doing things like MOOCs. Even with the limitations that exist on MOOCs, there's some kind of, it's cool to have so much data. Okay.
What if you had, so I'm thinking right now about just like linear hierarchical models with random effects. Say you have all this data, like you mentioned earlier, you have a class, and next semester's class, right? You have 2 semesters worth of data, but you don't necessarily care about the differences between those semesters. You want to know about this other pattern, but you do want to address the variance that might be there.
Right.
Is that?
So if you're just looking for a description and not a prediction of that other class, then you just join the 2 data sets together, and you can try and change things like time data. So I'm looking at time series data with this kind of method, and so you start to do things like how many days from start or how many days from exam, and not date of year, because that gets into problems. I did want to show you one other thing, and I don't know it super well, but I wanted to show it anyway. It is another data set that I put up last night. It's an ARF data set, which is very exciting. And in this data set, I have, it's just like the past data set, last data set, but I've changed the grade. The grade now is a numeric variable between 0 and 2.398, with a mean of around half, right? And so this is something that you might use a regression analysis on. And I wanted to show you a technique that I am exploring more often now.
Exactly what I was going to ask.
It's called classification 15_2.arf, and I put it up last night.
It's the only ARF.
Yeah, there should be only one ARF file there. It's not a great example because I was chatting with my daughter as I was making it, but I think it will suffice. So you jump into the classifier tab, you change to real grade as the piece that you actually want to classify. We'll leave it at cross-validation for now. If you hit choose, you'll see that J48 is now shaded out. WECA's got enough smarts to tell you that, oh no, that's a numeric value, you can't use this. But there's a value here called M5P. M5P essentially tries to create a decision tree on all of the attributes except the one you're trying to predict, and then for each leaf in the tree runs a linear regression analysis. analysis, right? So you end up with many linear models that are in the leaves of the decision tree. So you get this multi-level modeling opportunity. So we hit start.
And the more fancy the method, the more overfitting typically it does. But that's
right. Actually, to see a good example, we have to tweak some parameters of the tree as well. So we want to set the build regression tree to true, and I choose unprune. I don't want it to get rid of data. This is really just for demonstrating a number of instances, 10. You can learn more about all of these methods through, I think, capabilities or more info pops up, even cites to the papers of describing them.
How do you close them?
In Linux, I do this. It's sad, isn't it? And then we start. So we can see this is our tree. If your college is engineering, if your college is, not engineering, and your college is not computers, and your gender is not female, then use linear model 1. Otherwise, use linear model 2. And then you have the linear models here. And these are trivial examples. They're not very nice examples. It just says your real grade is going to be a 0.26. Here, your real grade is going to be a 0.31. And this is largely because the data, I just manipulated the data in Excel and didn't add a lot of variance and just wrote a formula to do it. And so these linear models, though, can be much more complex and take into consideration many of your numeric values. So you might have a lot of numeric values that feel like there's a linear relationship, but you also want some hierarchical modeling, and you don't want to do some polynomial regression and want to try something like this instead. I like it because it's very explainable still. You still have that high-level tree that you can explain that gives you maybe ties to some ed theory things, like we know learners like this do this. That sounds like a very classification, levels of a tree. And then the nitty-gritty of actually predicting the grade maybe tweaks on different campuses or different student bodies.
You can visualize this in the same way too?
I believe so. Yeah. It's kind of sad that they don't expand the linear models up here.
Yeah, that would be cool to put the lines there. That would be cool.
Yeah. Would have been nice to see. You could save the instance data. I wonder if I do that, if that helps. So here it just builds the model, but it doesn't relate the data, but you could just, that's the wrong one. You go up here, we just say save instances, true. That again. So right click. Oh yeah, but the instance data is not very exciting because it just lets, Weka's visualization tool is not great. Just lets you compare two variables on an XY plot. So Weka's kind of a neat tool. One of the other neat things of the tool is you see how this is kind of like awkwardly written with all these like minuses and dashes. Actually, that's because that's the exact line you could run on the command line with Weka to have it just work on your data automatically, right? So you can explore it through the GUI, and then when you want to like run it on 10,000 students nightly to generate models, you can just batch script this into Python or Java or whatever you want, right? So it's kind of cool in some ways that it's very easy to integrate that, where a lot of people give me their data or their SPSS output, and I'm like,
there were better ways of doing that. They should, for instance, that command line should be in the output, saying if you want to run this automatically, here is your line, and then provide normal people with normal options.
That's how they would learn, yeah.
Somebody who had a little money to spend on building a better interface for this would be, I think, make the product get adopted much. much better. So that's kind of in a nutshell how classification works. Right, so the most important consideration called overfitting, and this is really important. If you don't address this in your paper, it will get rejected, right? This is kind of the state now. If you say you did tenfold cross-validation, my mental classification is you have a 50% chance of making it through with that being enough. If you say you also had a holdout set of a certain amount that you ran right before submitting it, that's the gold standard right now. Even better is if that holdout set is highly representative of the way you would use the system. So I had 1 year of data, and on next year's data is my holdout set. That, I think, is really the gold standard for a predictive modeling system.
Especially if your standard is that you're going to do some data mining, implement, say, like a tutoring system, which you're then going to put out there. Having a completely new year set of data with new students is a great way of testing how it's been performed.
Yeah.
In a while.
And it gives you real performance, right? And I think that that's important. And so I think one of the things data-driven methods and kind of the computational methods of approaching this have done versus the statistical methods is there's not just a goal to try and help theory grow and change and be influenced by theory, but also to build pragmatic products on that theory. And that requires this noisy real world.
That was what actually, I don't know if you're familiar with the KDE app, the data
Yeah.
they did a few years ago. That was one of my problems with the way they ran it, was that their test set was just randomly selected student transactions. So you could actually use the student identifier as a factor, which doesn't really help you if you're trying to predict the behavior of completely new students.
That's right. That's right. I want to give it like a really good example of overfitting from my own work. So here's a model that we built. We wanted to produce to determine in a MOOC. We wanted to build a predictive model. We had something like 1,000 different attributes because we were doing this funky thing with time and time series. But we wanted to basically be able to say, are you going to pass or fail this MOOC? This dotted line is what we get with tenfold cross-validation, right? And so a kappa of 0.3, it's nothing to write home about, but that's on day one of the MOOC, right? So that's basically, if you showed up to the class on day one, we already have a better than chance, guess that you'll be able to pass. But it rises, fairly rapidly, and then, 0.9 kappas are amazing. This is great, I think, for especially such a coarse-grained prediction. When we held out, we trained on 2 years of data, and we held out the 3rd year of data as our actual test set. And you can see our kappa is much lower. The climb is similar, but not the same. And yet it continues to climb, right? So if you made your decision here that 0.8 was, enough for an intervention, you'd never actually want to use our prediction, because we never actually achieved 0.8, even by the end of the class. There's just so much variance, so many latents that are coming in.
In this context, you were trying to, this is really interesting. You're using a whole bunch of variables over time and trying to maybe see what variables are important for predicting whether or not you're going to stay in the MOOC. And so that way you could say, with your kappa point, 8, like you just said, at day 9, you'd be able to, let's intervene here.
That's right.
That's how you would use that?
Right. And we actually determined from this data that it wasn't until 3 weeks in that we should really feel the model is stable or doing a decent job, because kappa for most of our courses approached 0.5. That's still just a value judgment, though, on what kappa is appropriate, right? So there's something I like to call the Dawson principle, for those who know Shane Dawson. There's multiple different ways of being wrong. There's also multiple ways of being right? And so this comes down to that confusion matrix, understanding how you're right and how you're wrong, and trying to contextualize that. And so here's what that confusion matrix looks like over time. And so here are a number of students in the class. Our orange line here are the false negatives. We thought they would fail, but they didn't. Yippee. So these are the ones that we wasted their time, essentially, right? We gave them stuff that they didn't need. We also, the dotted green line, these are our true positives. These are the people that we thought would pass, and they did pass, so we didn't waste their time. And you see, we can't really distinguish as well between these groups until kind of day 15. We also have this giant jagged line, and these are our false positives. And these are people we thought would be successful, they're not. And that's our missed opportunity. Those are the people that you know, 3 weeks in, if we were doing an intervention, we're missing 8,000 people that need our help. And so that just contextualizes a little bit more kappa, right? As opposed to, you know, this number of 0.2, what does that mean? Where are you wrong, right? This tells us who we're wrong. And then of course the last value, the true negatives, these are people that we thought would not be in the class, or not get the certificate and weren't. I didn't graph it because it's almost everybody because it's a MOOC. And so most MOOCs people don't get certificates out of, right? And this really hammers home the need to use a chance-corrected predictive model, because very easily we have 90% or higher classification accuracy, but that's not a meaningful number because easy to.
So I had just a general question about Weka, but this might not be the time yet.
Oh, I think
all this,
I'm just about done.
Okay, I'll wait.
All good classification models are look-alike. Every bed is bad in some way, you know, like this.
No, they're all wrong. It's just some of them are useful.
Yeah, that's right. That's right. That's right.
Like,
okay, so some things to consider though, moving forward. Unbalanced data can produce unclear results. Actually, I would rather say balanced data can sometimes give you a really good model, and so that's something to think about. There's lots of different solutions. We touched on some of those, but this SMOTE is awesome. I like it. And of course, remember the assumption of independence of attributes. Most of these methods assume your postal code in your city or your zip code in your city have nothing to do with one another when that's not really true.
In classification, that's typically not a problem. Because imagine that you have two of the same, like, I don't know, let's say that sex and gender are the same. You know, in your data set, it turned out to be the same. It will ask a question, you know, are you a male? And that's it. The other one is totally, they're not bringing any new information. So it's not like it will inflate your errors.
It is a problem when you start to rebalance your data. That's when it's a problem. In the actual classification task, lots of attributes don't end up being used because they just don't add more value. Yeah. Lots of other places to go with data mining, data cleaning and transformation, and a whole kind of, you know, that could be a degree almost. Attribute selection, though, is what I think is the hardest thing, and that's where a lot of theory has implications to help us try and decide what features we should be gathering. Balancing of data input and its effect, and then ensemble models. And so these are models of models, and you start to do things like building multiple models to try and get away from overfitting of data. It's kind of cool stuff. I don't use it. I don't find I need to use it when I'm looking at the data.
The idea with that is basically, you know, decision rule will overfit in one way. The other classification neural network will overfit in another way. So you build all 5 of them and then do a majority vote. Like all 4 of them, you know, out of 5 models, 4 say the student is at risk. You say he's at risk. You're basically just, you know, using a brute force almost to do that.
I mean, computational power is cheap now, right? And that's really why it's come around. That's it. Yeah.
So I had a couple of, I guess, maybe a little bit more technical questions.
Yeah.
So one is, I seem to remember that Weka integrates with R, right, through script files or something?
Yeah, so actually R has the option to do you want Weka to call R or R to call Weka?
Well, R being the primary tool.
Okay, yeah, so there is something called RWekaJ or something like that, which is a way to integrate all of the functionality, all the classifiers and clusters inside of Weka into R. Keeping in mind that R will have a number of them already. These two will exist in R.
My second question, what are the, like, why Weka? What are the strengths of Weka, and what can Weka do that other tools can do? Or at which point would you want to consider switching to Weka given that?
Right. If you have a programming background, Weka is not necessarily the first place to go. If you don't have a programming background, it offers, I think, a very nice way in, right?
Actually, the latest version of Excel added a lot of data mining capabilities too. So all the products are starting to add these kind of computational approaches as opposed to just linear regression or Pearson correlation, which was kind of the norms. I like Weka because it's very scriptable, so I can explore in Weka, I can tweak things in Weka, and then I can just grab the command line and throw it in. And I do a lot of things through Python, but there's a Python library scikit-learn that I also use, which is great in different ways. Weka is...
When you don't know what you're going to use, I think that would be, you
Yes.
can fastly play around, explore 15 algorithms by just clicking around, and in R, it will be much more painful to
each package has to be installed separately.
That's been my experience with R. I think a lot of the algorithms, there's more consistency in how they've been implemented for Weka. In R, like, you get a huge range of some really high quality, like people put a lot of work into their package, and others it's just like, I threw this together for my own purpose, you can use it if you want, and it's like
That's
a
right.
lot of times they've got these assumptions baked into it, they're not as generalizable.
There's another tool, RapidMiner, that is used, and I know Baker uses it.
Yeah.
And the very first thing he says is download the Weka package to integrate into it, and uses the all the Weka modeling tools. And so if you watch his course, that's what he does. I think it's exactly that, right? Weka's got this diversity of libraries. It's kind of like VR for data mining specifically, just like people are attracted to R because it's got a billion libraries. It has, these little things like simple visualization, et cetera. It's getting a little long in the tooth, I think, like it's getting a little aged. Being acquired and integrated into Pentaho is, I think, interesting, and Pentaho and Kettle and that kind of stream that's coming through there is interesting too. The key is there's lots of, because it's been open source, there's a way to wrap it, put it into Java, a way to wrap it, put it into Python, a way to wrap it, put it into RapidMiner. So Weka has this whole experimenter interface. Knowledge flows, maybe what I wanted. Yeah, where you just start, dropping things on, and you can
building a pipeline of your.
Because that's like, as far as like feature building and some other things, are they easy to do in Weka? Or, I mean, like you said, you don't do your data manipulation.
Right. Josh Barron and their team at Marist, they're doing an open analytics project, and it's all open source. They use Weka and Kettle, which is kind of the open source version of Pentaho, and they use this method. Because I'm doing a lot of research analysis, I use Python scripts to do a lot of my data cleaning. Pandas as a data processing and data analysis library for that, and for inferential statistics, I use a lot of Pandas, NumPy, SciPy, that kind of thing. And then I use Weka when I want to.
So you feed like a clean CSV to Weka at that point? That's how they talk.
Yeah, that's how I largely use it.
Pretty much goes on like you know how to do it in Python. It's just a couple of lines of code to process it. Here you'll need to figure out in this messy interface where to click, what to do. It's just like not worth if you already know how to do it.
So Weka is not like a full pipeline. It's just for
it is.
finding.
It is, but I don't know many people who use it that way. Except for Josh Barron's group at Marist. They do. I think they use Kettle, which maybe is a sister project, or it's under that Pentaho BI umbrella. But yeah, I don't use it that way. I feel that the Python method is easiest, but I'm doing research analysis, right? So that's a little different thing. Right now, I'm working on one where we're deploying it all in AWS and trying to use Lambda functions and so forth to do this so that we can scale. So one of the nice things about being in Weka and just seeing this nice little line at the top, so I can just copy and paste that, add that fork in, and now I can test building, 100,000 models just with Lambda and just fire off all these different instances, come back and calculate the, kappas or whatever data it is I want to calculate for it. I'm looking at, now more of my research is looking at building daily models and trying to evaluate those, right? And so moving more towards kind of a real-time model and not the descriptive model. So I think that's one of the other challenges with classification, is often we build the classification model on all the data. If some of that data doesn't come till week 10, that might be too late to do anything about, right? So you have to think about when would you intervene, and only building a model on that amount of data that you have, which could would change your model quite a bit, because the models are across all of your attributes. So the example I showed, the reason the kappas start so crappy at 0.2 is because we literally have 1 day of data for a student. That's not really, it's better than chance, but not much better than chance at predicting their outcomes.
As MOOCs get shorter, more modular, you're going to have an even shorter window.
Yeah, it is, right? Almost all of our MOOCs have switched to 4-week MOOCs now, right? And that's challenging.
Yeah, what are you going to do about it? I don't know anything about it.
And so the interplay between demographic features that you can bring in and student activity features in the course, I think, is really kind of where the state of the art is at right now, as far as learning analytics modeling and modeling educational data in higher ed. So that's kind of a nice, right? You bring in all of this kind of theory-driven demographics data at the beginning, and you really use that as a bootstrap for the first several weeks in building your models, because you don't have much of the behavioral data. And then as you get behavioral data, you can emphasize that a little bit more.
I started and I dropped off a MOOC, which was, it just was too much effort, calculus MOOC. And because it's really, really like 12 weeks, very intensive course, they gave you a test, calculus test before start of the course. And that was cool. Like, okay, I didn't do this like for years. Like, how much I can do it here? And they do that. You can do something. I never seen that anywhere else being done. But like demographics and so on. But you can also sometimes even pre-test maybe if they want to do that. But they, it's optional. You can skip that and do it your own way.
I'm kind of excited about ASU's Global Freshman Academy that they've just launched with edX. So they're putting up 8 courses, and those courses cover the range of liberal arts. And the idea is you can take them for credit. But the cool thing about it is that now you have data points about students that aren't like just their final grades, but their interactions.
Doctor, I have 2 questions. The first, how do we prepare the raw data? So our data in the online learning management system. So how do we input the Excel?
Yeah. So I think that there's a huge need for basic data cleaning mechanisms. And so like at Michigan, one thing we're doing is we've created a data science institute, and that institute's going to have some help resources to help people kind of figure out how to clean their data. You could do some cleaning of it in Weka, but I don't think it's very sophisticated. So most of the students I'm working with, I get them to pick up Python and start to learn Python for data cleaning.
You will extract the data from database. You will somehow convert it to a cumulative data per, students. It's called, like tidy data. All students or observations are rows. All the columns are your attributes. And you don't have that in LMS database. So you need to get that through Python or any other script. Yeah. So you will make a script and see, student 1, you count how many times he did, and you put 1 attribute, and so on. So you basically manually. There is no automated way of doing that.
So the second is how do we predict using data? What's that predict model look like?
What does the model look like itself?
You construct by yourself and use data to.
Yeah, so it looks just like that tree of rules. Yeah, that's the model. And then you can save that model. And so they have special model file formats if you want to save it and run it on data in the future. If you want to put it in a paper, you can just put that tree in the paper. Or you can write your own software that uses that tree. The nice thing about the decision trees is fairly straightforward kind of, I think I taught a first-year computer science class and made them do decision trees, and not machine learning, but just to write a decision tree and have it make some decisions for a video game, right? And so it's a very, I think it's a very tractable kind of thing that you can take. It depends on how you want to use it, but if you want to integrate it into decision-making at the institution, I mean, these can be policy points too, right? They don't have to be kind of computational if you didn't want them to.
And we will use a classify function to predict.
Yeah, so the classifier will work with your training data and will help you choose, what you're going to, what attributes are valuable. It's going to build that tree and do the prediction.
Thank you.
Yeah.
Thank you. Yeah.
Well, feel free to help yourself to some more food if you haven't got a chance. And if you haven't already done so, please sign in. We'd be interested to have some information as we do future events in data mining and analytics.
You can use the position in which they sign in as a feature as to whether they would show up at another event. I'm just saying, if you wanted to build a predictive model.
Build a predictive model of whether or not you're going to show up.
Exactly. Could review the video and see how many people fell asleep.
Yeah.
Who was paying attention? Who was on Facebook? Great.
No.
Hey, just Linda. Well. Yes, I'm in New York too. We were there for a learning conference. It was at Columbia Teachers Hall. I presented a paper there. Is what? So this Columbia period. Yeah, New York. Oh, Manhattan is crazy. Yeah. Are you flat out on the drive? I'll be right back. Yes, sir.
Amy, did you talk to somebody about your show?
Yes, which I think has been booked. However, I just got a notification that the old one is still booked.
Oh, okay.
So I was going to try and catch the lady that.
I think Justin also has.
Yes.